Okay. Last lecture you have learned the Laplace transform. The Laplace transform for ft is equal to the integral of ft exponent negative st dt from 0 to infinity is equal to fs. And you have learned that Laplace transform for a is equal to a over s. Exponent at is 1 over s minus a. Sin at is a over s squared plus a squared. Cos at is s over s squared plus a squared. Hyperbolic sin at is equal to a over s squared minus a squared. Hyperbolic cos at is s over s squared minus a squared. And then the Laplace transform for t power n for positive integer n is equal to n factorial over s to the power n plus 1. And then this is the first shift property. In the Laplace transform for exponent at ft is equal to fs minus a. And this is a multiplication by t power n property is equal to negative 1 to the power n dn dsn fs. Okay, and today we are going to learn the division by t property, which says if Laplace transform for ft is equal to fs, then Laplace transform for ft divided by t, that's why we call division by t, is equal to the integral of fs ds from s to positive infinity. Okay, provided the limit for ft over t when t approaches 0 exists. Okay. To prove the Laplace transform for ft over t equal to the integral of fs ds from s to infinity. Okay, let's start from fs is actually the Laplace transform for ft and is equal to exponent negative st ft dt from 0 to infinity. This is from the definition of Laplace transform. Okay, later on we integrate both sides by integrate respect to ds from s to positive infinity. So we integrate fs here from s to positive infinity respect to ds. So the same thing with the definition of the Laplace transform here. We integrate from s to positive infinity respect to ds. Okay, later on we interchanging order of integral as s and t are independent variable. Okay, when we exchange the order of integral means here the ds. Okay, we move in here. So mean we integrate exponent negative st respect to s and the limit for s from s to positive infinity. Yeah. In this one, move in here. So integrate exponent negative st respect to s. Respect to s. Hence t is a constant. So integrate exponent negative st respect to s. We get exponent. This is negative st divided by negative t. Okay. Then evaluate it from s to positive infinity. This is what here. Okay. So we concentrate. This is where evaluate respect to the s. So plug in the upper limit. So e negative infinity t will be equal to 0. Okay, and then plug in the negative lower limit, which is equal to s. Okay, remember we integrate respect to s, so we put it into variable s. That's why. And then so this is minus because this is minus. Okay, this is a lower limit substitutions. Then we s. Put it into the s here because we integrate respect to s. That's why you get back minus exponent negative st over negative t. And then negative become positive. Okay, outer we still have the integral respect to t, exponent negative st. So here, this become ft over t. Then by definition, okay, of Laplace transform, is actually Laplace transform for ft. So we integrate exponent negative st multiply with ft dt from 0 to positive infinity. So here you notice this one is here. So this is the same integral, only ft replaced by ft over t. Hence, this is actually the Laplace transform for ft over t. And the left side is actually the is the integral of fs ds from s to positive infinity. So this is a division by t property. In the Laplace transform for ft over t, then identify your ft, take the Laplace transform, you get the fs, and then you integrate respect to ds from positive s to positive infinity. Okay, example 1. Find the Laplace transform of sin t over t. Sin t over t. Okay, before we can find the Laplace transform, we have to make sure that the limit for this is ft. Okay, this is in the form of ft divided by t. So you have to make sure that the limit for sin t over t when t approaches 0 exists. Okay, so to find the limit, okay, if you substitute t by 0, sin 0 you have 0. So the denominator also 0. So this is the intermediate form. Hence, we apply the L'Hopital rule, where you have the intermediate form is of the limit either 0 over 0 or infinity over infinity, where you can apply the L'Hopital rule, which says that if limit for ft gt when t approaches 0 is in the form of 0 over 0, okay, or when t approaches infinity is in the form of infinity over infinity, then you can find the limit, okay, when the t approaches 0 by differentiate numerator and denominator separately. So in this case, limit for sin t over t when t approaches 0, sin is in the form of 0 over 0. Then we apply the L'Hopital rule, where you differentiate sin t, you have cos t, differentiate t, you have 1. Now you plug in t equal to 0, cos 0 is 1, so 1 over 1 you get the answer 1, hence limit exists. Okay, if the limit exists, then you can use the division by t property, okay, which says that if Laplace transform for ft is fs, then Laplace transform for ft over t will be equal to the integral of fs ds from s to positive infinity. Where if you identify here, means the ft is equal to sin t. Yeah, if you compare this form, ft which is in numerator is equal to sin t. Okay, and then to get the result of Laplace transform of ft over t, you need to find the fs. Fs is actually you take Laplace transform for sin t, you have 1 over s squared plus 1. Okay, lastly, to get the Laplace transform for sin t over t by applying the division by, this is by t property. So you will have integral of fs, which is 1 over s squared plus 1, ds from s to positive infinity. Okay, you will get the answer is arctan s. So, evaluate from the limit s to positive infinity. So, you arctan infinity minus arctan s. Okay, arctan infinity you get pi over 2. And this is the arctan s. Okay, maybe recall back how we get the result of this integral, which is to arctan negative s. Okay, this one you can use the trigonometric substitution, where you let s equal to tangent theta, ds will be secant squared theta d theta. So you substitute ds by secant squared theta d theta. S is tangent theta, so s squared will be tangent squared theta plus 1. Okay, and noted tangent squared theta plus 1 is actually equal to secant squared theta. This is equal to the secant squared theta. Hence, okay, you cancel out, just become the integral of theta, 1 d theta. The answer will be equal to theta, where from here, they give you theta is arctan s. Okay, and how we knows that? The arctan infinity you get pi over 2. Okay, this is a graph of arctan x. You notice when x approaches positive infinity, okay, the arctan x actually this is approaches pi over 2. Okay, so that's why the result for arctan sin t over t is equal to pi over 2 minus arctan s. Okay, the second example finds the Laplace transform for hyperbolic sin t over t. So similarly, before you can evaluate the Laplace transform, you have to confirm that the limit for sin t over t when t approaches 0 exists. So to evaluate the limit, you plug in t equal to 0 into the function sin t over t. Okay, or we can change the hyperbolic sin t to the exponent t minus exponent negative t divided by 2. So means sin t is actually exponent t minus exponent negative t divided by 2. And then here initially you have the t. Later on you plug in t equal to 0. So exponent 0 is equal to 1. Again, you plug in t equal to 0 to exponent negative t, you still get exponent 0, which is also equal to 1. So the numerator, you get 0. Of course, the denominator, when you plug in 2t by 0, you get 0. Again, this is intermediate form, which is 0 over 0. Hence, you apply the L'Hopital rule, where you differentiate numerator and denominator separately. Don't use quotient rule of differentiation. For L'Hopital rule, you just differentiate numerator, denominator separately. So you differentiate exponent t, so you get exponent t back, and then you differentiate exponent negative t, you get negative and minus here become positive exponent negative t. Differentiate 2t, you have 2. Now, plug in t equal to 0. So, exponent 0 you have 1. Plus, exponent negative 0 also 1. So, 2 divided by 2, the answer is 1. So, limit exists. Hence, you can find the Laplace transform for sin t over t by divisions by t property, which give the integral of fs ds from s to positive infinity. To get fs, identify your numerator, which is the function of t, ft. Okay, here ft is hyperbolic sin t, which is equal to exponent t minus exponent negative t over 2. Okay, so this is a ft. Identify a ft and then find the fs. Okay, find the fs and factor out half. So Laplace transform for exponent t is 1 over s minus 1. So minus. Laplace transform for exponent negative t is 1 over s plus 1. Hence, the Laplace transform for sin t over t by using division by t property will be equal to the integral of half, the fs is here, half of 1 over s minus 1 minus 1 over s plus 1 ds from s to positive infinity. Okay, and you integrate it, you get here, this one. Integrate 1 over s minus 1, you get ln s minus 1. So this is minus ln s plus 1. And the limit from s to positive infinity. And you combine these two ln using the formula ln A minus ln B will be equal to ln A divided by B. So hence this become half of ln S minus 1, okay, divided by S plus 1. Okay, if we directly plug in the upper limit, it yields to, okay, mean if we directly plug in the upper limit, okay, here, so we have ln infinity minus 1, of course you get infinity, and then this is infinity plus 1. So we are not sure, okay, look like it's in the form of infinity over infinity, but outside you have ln. So I'm not sure the result is what. So to evaluate the, okay, upper limit substitution, what we did is actually we divide each term in the lns here by S. Okay, divide by S. So S divide S, this is 1, this is 1 here. Now we substitute the upper limit. So here. So minus, okay, substitution of S. Okay, you notice this term is actually, we verify from here, ln S minus 1 over S plus 1. So if you plug in the S, okay, you get back the same term, which is ln S minus 1 over S plus 1. Which is here. Then you get 1 divided by infinity, you have 0. So this is also 0. So later on, the first term here you get ln 1, which is equal to 0. Then this is left, negative ln S minus 1 over S plus 1. Okay. So we expand back the ln here. So this become minus, okay, the bracket, ln S minus 1 minus ln S plus 1. So expand the negative in. So this become plus. Then we combine back, this become ln S plus 1 over S minus 1 because minus here. Okay. Hence, this is a result for Laplace transform of hyperbolic sin t over t. Okay. Lastly, the third example, find the Laplace transform for cos 2t minus cos 3t over t. Okay, notice that it's in the form of ft over t. So before you can apply the division by t property, you have to check if the limit ft over t or the cos 2t minus cos 3t over t when t approaches 0, okay, the limit exists or not. So by direct substitution of t equal to 0, cos 0 you have 1, so you have numerator here 1 minus 1, which is 0, of course. Plug in t equal to 0 into denominator, you get the answer 0. So again, it's in the form of 0 over 0. Then you can apply the L'Hopital rule, mean you differentiate numerator and denominator separately. So you differentiate cos 2t, negative 2 sin 2t. Differentiate sin 3t, you have negative and minus, so become plus 3 sin 3t. Differentiate t, you have 1. Okay, now you plug in t equal to 0. Sin 0, you have 0. Okay, sin 0 is 0. Okay, that's why 0 divided by 1, you have 0. Okay, hence limit exists. So you can find the Laplace transform for cos 2t minus cos 3t over t, okay, which is in the form of ft over t. Will be equal to the integral of fs ds from s to positive infinity. So identify the ft here is cos 2t minus cos 3t, and then to get the result you have to find your fs, which is Laplace transform for cos 2t minus cos 3t. So we'll get s over s squared plus 4, so minus s over s squared plus 9. Hence, by division by t, okay, property, the Laplace transform for cos 2t minus cos 3t over t will be equal to the integral of your fs is from here, ds from s to positive infinity. And then to integrate here, okay, we make use of the integral of f prime s over fs ds will be ln, okay, fs, ln fs. So you notice that if the denominator here, this is fs, okay, numerator, okay, if we differentiate this one, we should have 2s. Hence, we multiply 2s, divide by 2s. Similar with the second term. So, the integral is in the form of integral of f prime s over ss ds. Hence, the result will be ln fs. So, the result is half of ln s squared plus 4. Okay, so this is a bracket. So, minus ln s squared plus 9. Okay, it combine these two ln, become ln a over b. So, it become ln s squared plus 4 over s squared plus 9. Okay, from the limit s to positive infinity. Against, okay, direct substitution into here for the upper limit. We are not sure what is the limit result because it's into the form of ln infinity over infinity. Hence, okay, we divide, okay, by the highest, okay, s squared term, which is s squared in each term inside the ln. So we divide, okay, s squared, s squared, s squared, s squared. Okay, so s squared divided by s squared, this is 1, this is 1, so this become 4 over s squared, this is 9 over s squared. Okay, now we plug in the upper limit here. So this term is either from here or actually initial form here. Ln s squared plus 4 over s squared plus 9. Minus because minus substitution of lower limit. Okay, so for the over infinity you got 0, 9 over infinity have 0. So this again you get ln 1, which is 0. Okay, and then we have here negative. And we expand back ln, okay, s squared plus 4 over s squared plus 9 become ln s squared plus 4 minus ln s squared plus 9. And then we expand the negative inside the bracket here. So this minus, this is negative, negative, positive. And we combine back, okay, these two terms. You get half of ln s squared plus 9 over s squared plus 4. Okay, with this, thank you, okay, for attention and watching.